Hello. Welcome back to the RedMars Podcast. I'm your host, Astro Jake, and today we're diving into a topic that is so mind-blowing, so essential, that without it, humanity would have never reached the moon, sent rovers to Mars, or even unlocked the secrets of the universe. Yep, we are talking about computers in space. So let me set the stage for you. The year is 1969. Apollo 11 is descending towards the moon's surface, and suddenly, boom, an alarm. It's error code 1202. The astronauts don't know what it means, and time is ticking. The mission could fail. History could be rewritten. But, back on Earth, a team of engineers know exactly what to do. They calm the astronauts, give them the go-ahead, and just moments later, beep, 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 the Eagle has landed. This moment, and countless others like it, were made possible by space computers, the silent, brilliant brains behind every great leap we've made into the cosmos. But what does it take to build a computer that can survive the harshest environment known to humanity? Today we'll explore the history, challenges, and future of these incredible machines, from Apollo's primitive circuits to the AI revolution powering today's missions and beyond. Buckle up, listeners, we're about to take off. Let's take a journey back in time, to the dawn of space exploration, and discover how computers became an integral part of our ventures into the cosmos. Back in the 1960s, computers weren't the sleek, lightning-fast devices we carry around in our pockets today. They were room-sized, behemoths, massive, slow, and finicky by today's standards. Yet these machines became the backbone of one of humanity's greatest achievements, landing on the moon. Let's talk about the Apollo Guidance Computer, AGC, one of the most famous early space computers. This marvel of the 1960s engineering weighed about 70 pounds, had about 4 kilobytes of RAM, and operated at a clock speed of about 0.043 megahertz. To put that into perspective, even the simplest modern smartwatch is millions of times more powerful. But don't let its specs fool you. The AGC was revolutionary. It introduced cutting-edge innovations like integrated circuits, which were rare at the time, and used rope memory, a type of read-only memory literally woven by hand by skilled technicians, many of whom were women. Every wire threaded through or around a magnetic core represented a 1 or a 0, creating a form of data storage that was incredibly reliable for its time. Fun fact on this, my father actually has one of these pieces of memory in his workshop that he keeps. That's pretty cool to see what actually went into this kind of work that actually built these types of memory devices way back when. Alright, continuing on. The AGC also featured an iconic interface called the DSKY, pronounced DISKY, short for Display and Keyboard. This device allowed astronauts to input simple commands using numerical codes and receive real-time feedback from the computer. Astronauts like Neil Armstrong and Buzz Aldrin relied on the AGC during critical moments like the final descent of the lunar lander. In fact, during the Apollo 11 landing, the AGC issued the now famous 1202 alarm, a warning about an overloaded processor. Despite this, the computer continued to function as intended, prioritizing essential tasks and enabling the first humans to touch down on the moon. Fast forward to the 1980s, and the Space Shuttle program, and we see massive leap forward in space computing. The shuttle avionics system featured 5 general-purpose computers, each equipped with 104 kilobytes of memory. While these specs might still sound modest, the system's design was groundbreaking. The computers worked in a redundant configuration. 4 were programmed to work in unison, performing the same calculations and cross-checking each other, while the 5th acted as an independent backup with separate programming. This ensured that even in the event of a failure, the shuttle could continue its mission safely. It was humanity's first step toward creating reliable, reusable spacecraft, a foundation for today's commercial spaceflight industry. By the late 1990s and early 2000s, space computers became even more advanced as humanity set its sights beyond Earth. Take, for example, the computer on board Mars rovers like Spirit, Opportunity, Curiosity, and Perseverance. These machines are light years ahead of the Apollo era, featuring radiation-hardened processors like the Rad 6000 or Rad 750. These computers can process data at speeds of up to 200 megahertz, not blistering by Earth standards, but more than enough to be capable and enable rovers to navigate autonomously, analyze soil samples, and even perform tasks like drilling and taking selfies. What's even more impressive is how far we've come in terms of software. Early computers required punch cards or simple command interfaces. Today, spacecraft rely on advanced algorithms capable of performing real-time decision-making. For instance, Perseverance's computer doesn't just follow pre-programmed instructions. It uses artificial intelligence, AI, to autonomously map and avoid obstacles on Mars, the unpredictable surface. Let's also not forget the role of the international collaboration in advancing space computing. The computers on the International Space Station, ISS, are a mix of off-the-shelf and custom-built systems. They are designed to handle everything from managing life support systems to running scientific experiments. The ISS represents a turning point where space computers weren't just tools for exploration. They became essential for long-term human habitation in space. And today, we're standing on the shoulders of these giants. Space computers have evolved alongside humanity's ambitions, enabling us to go farther, stay longer, and do more. From the moon to Mars and beyond, these machines are as much a part of the story as the astronauts themselves. It's incredible to think how much has changed since the days of the Apollo guidance computer. Each step forward in computing power has been a step forward for humanity in space. And the best part? We're just getting started. Now let's dive deeper into the challenges computers face in space, because, let me tell you, it's no picnic up there. First, there's the constant threat of radiation. Out in the vacuum of space, there's no atmosphere to shield electronics from cosmic rays or solar radiation. These high-energy particles can wreak havoc on computer systems, not just people and astronauts in space. So this is also something we have to think about for these computer systems. What happens is, you can actually flip a single bit of memory, a phenomenon known as single event upset, which can change a 0 to a 1 or vice versa. This might not sound like much, but when you're dealing with a mission-critical system, a single flipped bit could cause anything from minor glitches to catastrophic failures. Imagine if your spacecraft misinterpreted navigation data because of a single bit error. It could mean missing your target by a planet entirely. That's where radiation-hardened processors, like the RAD750, come in. This robust little chip, which is based on the architecture of an old-school PowerPC processor, is built to endure radiation levels that would fry any laptop or smartphone here on Earth. It's used in spacecraft like Mars rovers and the James Webb Space Telescope. But this toughness comes at a cost, both in terms of money itself and in processing power. While your smartphone might run at several gigahertz, the RAD750 operates at a modest 200 megahertz. Why? Well, because reliability is far more critical than speed in the harsh environment of space. These processors aren't just surviving, they're thriving, operating reliably for years or even decades. Next up, temperature extremes. So space is a place of contrasts. In direct sunlight, temperatures can soar to over 120 degrees Celsius or 248 degrees Fahrenheit. While in the shadow of a planet or spacecraft, they can plummet to negative 100 degrees Celsius or negative 148 degrees Fahrenheit or lower. These wild swings in temperature can cause components to expand and contract, potentially leading to material fatigue and failures. Spacecraft computers are designed to handle these extremes, often housed in temperature-controlled compartments and paired with thermal radiators to dissipate excess heat. And then there's power consumption. In space, every watt is precious. Unlike Earth, where you can just plug into the wall or recharge with ease, spacecraft have to make it do with limited energy resources. Most rely on solar panels, which need to be lightweight yet efficient, or on radioactive isotopes and systems like radioisotope thermoelectric generators, RTGs, for missions venturing far from the sun. Computers on spacecraft are therefore designed to be ultra-efficient, capable of performing complex tasks while sipping power. Imagine running your laptop continuously for years on a single charge. That's the level of efficiency these systems aim for. Another major challenge is size and weight. Every gram on a spacecraft matters because of launch costs. For reference, launching a kilogram into low Earth orbit costs thousands of dollars. Space-grade computers must pack a lot of capability into a small lightweight package. Compactness and modularity are key designing systems that are easy to integrate and fit within tight confines of a spacecraft. Think of CubeSats. Those are very small satellite systems, very capable and cheap in terms of, or I guess relative to larger satellite systems. So universities and that usually work with CubeSats for their experiments in LEO orbits. But let's not forget maintenance, or I guess lack thereof. Here on Earth, if a computer crashes or malfunctions, you can call IT or swap out the hardware. Have you tried turning it off and back on again? In space, you're on your own. That's why spacecraft computers are built with multiple redundancies. If one system fails, another just takes over seamlessly. For instance, the Hubble Space Telescope has several backup computers and memory modules, allowing engineers on Earth to switch to a backup if something goes wrong. Finally, let's touch on data transmission. Even the most advanced computer is useless without a way to send its data back to Earth. The farther you go into space, the slower and more delayed your communications become. This means that spacecraft computers often need to do a lot of the heavy lifting themselves, processing raw data, prioritizing what's important, compressing it, and then transmitting that data. On missions like Voyager or the Mars rovers, onboard computers work tirelessly to make sure only the most valuable data is sent home. So as you can see, computing in space is no easy feat. It's a delicate balance of power, durability, efficiency, and redundancy. Every line of code and in every circuit has to account for challenges that would make the most earthbound systems crumble. But thanks to decades of innovation, we've built computers that don't just survive in space, they are able to thrive. Now, what about the role of AI and automation? We definitely want to touch on this just a little bit, especially in the day and age that we're in right now, where AI is exploding. So it's not just about surviving and thriving when it comes to AI. Today, AI and automation are transforming how we explore space. Take Perseverance, for example. Its AI allows it to navigate the Martian surface, avoid obstacles, and identify interesting rocks for study, all without waiting for a command from Earth. And then there's this Simon, C-I-M-O-N, the floating AI assistant on the International Space Station. It's like Alexa for astronauts, but way cooler. Simon can answer questions, display information, and even detect the emotional state of astronauts to provide support during long missions. Maybe a little bit creepy, but when you talk about the emotional stability of individuals that are secluded or removed from the social aspect of life, such that, or like that in space exploration, not as much on the ISS because you do have coworkers, but it is a great way to build somewhat of a connection, even though it's with a robotic creature. I guess I wouldn't even say creature, robotic thing. But I think this is definitely going to be key for developing some sort of social aspect for long duration missions that may be more secluded or smaller in size compared to, say, like a Starship mission going to Mars where you have quite a lot of people on board. There may be some other more deep space missions that are smaller in size, say 2, 3, 4 astronauts, and having a social companion, robotic or not, might help with some of the mental health for those types of missions. Anyways, we'll continue on here. So, in the future, AI will enable even greater autonomy. Imagine a spacecraft adjusting its course mid-journey, repairing itself, or even making first contact with alien life. Possibilities are endless, and as we approach that artificial general intelligence, who knows? But let's talk about edge computing then. Edge computing is a game changer for space exploration. In traditional missions, raw data collected by spacecraft is sent back to Earth for processing. While this works for nearby missions like those on the moon, it's not ideal for deep space exploration. As you venture farther out, think Mars or beyond, the delay in communication becomes significant. For Mars, it's about 20 minutes one way, and for destinations farther out, it could be hours or even days and beyond. Just think about a light year and what that actually means. That means in 1 year, light will travel that distance. And if we think about RF communications, which follows the electromagnetic spectrum, it moves at the speed of light. So when we send something at the speed of light to Mars, that takes 20 minutes. So now if we're looking at like Centauri and stuff like that, that is farther away in the light years. Well, if we ever get a spacecraft out there, we want to communicate with them, it'll take that time, that 1 year for that data to transmit there, and then the same amount of time to get it back. So there's got to be a better way. I think I mentioned in one of my previous episodes about quantum entanglement and quantum communications. Definitely could be the answer here. But for now, we are confined to the physics of the speed of light. So, edge computing. Enter edge computing. This approach equips spacecraft with advanced onboard processors that can analyze data in real time. Take Perseverance on Mars. For instance, its onboard processors allow it to sift through gigabytes of imagery and sensor data, prioritize what's important, and then send back only the critical bits, literally the bits. This not only saves bandwidth, but also allows the rover to act autonomously, whether avoiding a sand dune or drilling into, say, a promising rock formation. Then there's quantum computing. A revolutionary leap forward. While still experimental, quantum computers could one day tackle the challenges that today classical computers simply can't. Imagine using quantum algorithms to simulate complex planetary atmospheres in real time, optimize interstellar travel trajectories, or even predict potential landing sites on a distant exoplanet. The ability to process and analyze enormous data sets instantaneously would redefine how we explore space. Also, quantum computing possesses a different risk in terms of security, which I think we should go into on another episode where we can dive a bit more into just the quantum world alone. And maybe I'll bring my brother to come speak. He actually just completed his defense of his PhD in particle physics, so that might be a good guest to get on the show to talk a bit more about that. So, what about the computers in practice? Redundancy, reliability, and hobbyist options, kind of like that I mentioned for the technologies used in CubeSats at a university or educational level. So let's talk about how these computers actually work in the field and how advancements are making them more accessible. One of the critical considerations for computers in space is reliability. Space is unforgiving, as we've mentioned, and a single hardware failure could jeopardize an entire mission, an expensive mission. So redundancy is built into nearly every single system, at least those that are critical. For example, let's go back to Hubble. The Hubble Space Telescope has multiple backup systems for its onboard computers. If its primary computer fails, the backup takes over. Similarly, on the Mars rovers, they carry redundant circuits, processors, and memory units, ensuring that they can continue their mission even if one component malfunctions. This philosophy of no single point of failure is essential for deep space missions where repairs just aren't an option. But redundant comes with a cost. So radiation-hardened processors like the Rad 750 used in many space missions can cost upwards of $200,000 per unit. That's a bit more than your i7 or i9 processor, or even your most expensive NVIDIA chip that you run for your AI development or gaming computers. So these chips are built to withstand extreme radiation and operate reliably in temperatures ranging from negative 55 degrees Celsius to 125 degrees Celsius. However, their high cost means they're often reserved for just those critical systems. For missions on tighter budgets, like CubeSats, engineers are turning to cheaper alternatives, such as commercial off-the-shelf or COTS hardware. COTS components are mass-produced and affordable, making them ideal for smaller experimental missions. For example, CubeSat builders often use Raspberry Pis or Arduino boards as the brains for their spacecraft. While not radiation-hardened, these systems are incredibly versatile and affordable. Hobbyists can even pair them with open-source software to control everything from camera systems to attitude control. You can even run some of these systems in parallel, so you have redundant computers, so 2 Arduinos, 3 Arduinos, maybe 2 Raspberry Pis, and have them run in sort of what we call an active-active solution. So companies like SpaceX and Planet Labs have also embraced the idea of redundancy over radiation hardening. Instead of relying on expensive, hardened hardware, they use multiple COTS processors and rely on error-checking software to ensure reliability. If one processor is hit with a cosmic ray and causes glitches, then the other one takes over seamlessly. This approach has dramatically lowered the cost of building and launching small satellites. Speaking of accessibility, Organizations like NASA have open source projects, like OpenSatKit, which allows hobbyists and small teams to design and simulate spacecraft missions. Combined with platforms like CubeSat Shop, which sells everything from solar panels to reaction wheels, the dream of building your own satellite is closer to reality than you might actually think. Using tools such as SendCutSend or other hobbyist-style resources or services to, say, machine metal or laser cut or print different types of objects if you don't have a 3D printer, you can get a lot of these structures or design your own even using things like Fusion 360 at a very low cost. I did one for a small single U, 1U CubeSat, which means it's about 10 centimeters cubed. And I think the total cost of the structure itself was about $50, and that is built out of ionized aluminum. And looks super cool, super cost effective, and actually functional. So if you're interested, lots of resources out there. You can do it at a lower cost. And if you have any questions, absolutely reach out. I've done this before and I've worked with others, so I'd be happy to share with you my experiences and resources that I've used to do something similar. So whether it's $1 billion flagship mission using cutting-edge quantum computers or high school students launching CubeSats built with Raspberry Pis, computers are the beating heart of space exploration. They're what allows us to push the boundaries of what is possible, from Mars rovers analyzing rocks to CubeSats photographing Earth from low orbits. In the future, who knows? Maybe you, dear listener, will design a satellite or a program in AI that helps humanity explore the stars. The tools are becoming more accessible, and the technology more powerful, and the possibilities, well, that's endless. As we look towards Mars and beyond, computers will be the backbone of our colonies. They control life support systems, manage resources, and even grow food. Autonomous robots could build habitats before humans even arrive, while AI assistants help settlers adapt to the life of a new planet. And what about governance? Could Martian colonies rely on blockchain for their economy? Could AI oversee colony logistics to ensure fairness and efficiency? The idea of building a society from scratch is as thrilling as it is daunting. So let's just think about this for a second. In your everyday life, look around you as you're driving to work, sitting in your office, even at the gym, and just imagine if there were no computers, what would you have around you at this moment? You wouldn't even be able to listen to this show right now. So when you're starting out new on, say, Mars, or starting a new colony, say, on the moon, all these systems that we take for granted today, you need a computer. So we're going to have to bring these systems with us and eventually manufacture them with computers to create computers in these colonies. And it's super cool to think about that I can go on Amazon or Adafruit or any of these types of hobbyist resources that exist today and go and purchase, say, an Arduino or Raspberry Pi. Raspberry Pis are going up in cost right now. They are extremely powerful little systems and very capable, but not necessarily what is needed to kind of get into the development of one of these CubeSats, but definitely a good single board computer that allows you to run full-blown Linux or other operating systems. But an Arduino or even an ESP32, which combines the ability of, say, I won't say real-time because I don't think all of them support real-time operating systems, which we can go into a bit more as well, but they offer a platform to do development both through GPIO, and GPIO is a general purpose in and out, which is think of a pin that can either give a 1 or a 0, high or a low, and you can use these pins to manipulate different sensors or read sensor data or different peripherals to the board. So if you're building a robot or something like that, but it also, an ESP32 gives you the ability for wireless communication. So that's both through Bluetooth and Wi-Fi and different RF frequencies and that. So you can have a lot of fun with these boards. I've used them in steering wheel projects in my car to pass communications from a steering wheel to a dash in the car. I've used them for manipulating different strips of LEDs wirelessly from a Wi-Fi connection where it puts out a website for a user, and you'll connect to the exposed Wi-Fi connection, and then from there you are directed to a web page where you can manipulate the color of these LED strips. All these projects are very well documented, and resources are abundant, both YouTube or just Google searches. You can even use these AI tools today. You could go on ChatGPT or other AI platforms that you prefer and ask the program, hey, if I were to write a program using a ESP32 and I wanted to manipulate a specific driver LED strip or whatnot, just so you have to, if you get more specific with your prompts that you pass to these AI systems, they will be more accurate in the code that they produce or the resources they provide you. So it's almost an art of learning how to speak to these AI systems, at least at this point, so that they understand exactly the data they need to provide to you. So you can use these systems to help you learn how to write this code, how to build these projects, find other resources and that. So it's a great tool for those that are learning today. So really the only thing limiting you at this point is your own ambition, your own imagination, and maybe some financial part there as well. But in terms of cost, you could give up drinking coffee for a week and you'd be well on your way of building out your first CubeSat. So if you don't believe me, ask, and I can do a whole episode just on a CubeSat and what goes into the cost of that, breaking down what I've used for mine and talk from there. So with that, I won't talk your ear off anymore about these different systems, and let's get to the conclusion of today's episode. So from the Apollo guidance computer to the AI-powered rovers, computers have been our silent partners in exploring the cosmos. As we look to the future, they will be even more important than ever, enabling us to push the boundaries of what is possible. So we conclude today's episode of the RedMars Podcast, and this is one of our first deeper dive into a specific space technology. Again, not going entirely down to the technical nitty-gritty of what it could be. And I'll leave a poll for this one. So if you are interested in me going even deeper into the technologies about, which processors, the actual boards, the actual systems, and all that beyond what we spoke about today, let me know, and I'd be glad to do that. If you're interested in an episode just on CubeSats and what goes into making one of those, I think that would also be a great episode to chat with you folks about. So definitely let me know. So next week we'll explore another groundbreaking system. So be sure to subscribe, stay tuned, and follow along. Until then, as always, stay curious and keep looking up. Take care.